So let's get started. Myself, Amit Kesarwani. I'm a solutions engineer with a company called Treeverse. Treeverse is the company behind the product called lakeFS, which is an open source system. And lakeFS is more like a version control of data product. Like think of a Git for data. So I think nowadays everybody is talking about ML, AI, ML use cases. But ML evolved over time, like it evolved in around 70 years. Like in the 50s and 80s, it was still in the lab. Like in 1950, Alan Turing was the first one who created a test called Turing test, where he wants to see whether a computer can behave like a human being. And he created a machine to decipher decrypt the messages, encrypted messages. So that's how the kind of AI ML started in 1950. And then in 1959, Arthur Lee Samuel, he phrased the term ML. So that's far it goes. And then in 1959, again, Frank Rosenblatt, he invented a perceptron algorithm, which is more as the supervised learning for binary classifiers. So that came in 1959. And then in 1980s and 2000, the things started coming out of the lab into reality, more in the world. And people start thinking about the neural network. And the paper was published on random decision forest by scientist Tin Cam Ho. And then later on, another paper published in 1995 on support vector network, which is more for the algorithm for supervised learning for classification, regression, as well as outlier detection. So that came out in 1995. And in 1997, a lot of people you might know, like IBM came with the Deep Blue computer, which defeated the chess champion in 1997. So that's how it was evolving, and slowly ML was coming into the real world. But from 2000 and 2010, the more it came into the business world. It started coming into the business world. And if you remember .com time, a lot of data was generated. So ML was moving from knowledge-oriented to more data-oriented product. And in 2009, Netflix had a competition where a team called Bellcore's Pragmatic Chaos, they won a $1 million prize for coming up with the algorithm which was better than the Netflix recommendation engine. So slowly, business started getting interested into ML and how they can utilize into their business. And in 2010, there was a company called DeepMind started in UK. And in 2014, Google acquired it for $500 million. And that company, DeepMind, came up with this AlphaGo product, which was a computer to beat a champion in the Go game. So that was in around 2010 timeframe. And now we are in the modern ML space where a lot of things are happening, a lot of new innovations are happening. Like with GPU, a lot of compute power came in that. Like in the past, it was very hard to compute all those things. It was taking a long time, but GPUs made it possible to compute in parallel. And then Google came out with their speech recognition software. Facebook came out with their deep face recognition. And then now we all know about OpenAI, the GPT, and now Sora is the new one. So it's evolved, ML evolved over time in 70 years. And now in the current, like a lot of business are trying to use ML mainly for three different objectives. One is reducing the cost in the business. Second is getting the customer insights and intelligence from the data. And also like improving the customer service. Like how can they improve the customer experience? So that's the current state. Those are different objectives companies are working on. And the future is ML for everyone. Like cloud is making that possible. Like you don't need to have your own compute. You can run everything in the cloud. So all this AWS, Microsoft, Google, they are making the auto ML possible. And in the future, it's going to be more prescriptive kind of solution. And ML will be for all the businesses, you will be using ML. But also in the future, the low environment impact also will be focusing on the ML side. Right now, if you want to train ML model, the CO2 emitted by the training the model, all the compute power that you use, it's about 5 times the amount of CO2 emitted by a car in the whole life of a car. So right now we are using a lot of like compute power. So in future, we will be looking into more low environmental impact ML solutions. So that's how the ML evolved over time. As I mentioned earlier, it's evolved from knowledge to knowledge-driven to more data-driven approach. So there's a lot of data people use for the ML training purpose. So that's where my talk is focused around more data and how you should architect your data systems so it can be utilized easily by ML users. The challenge with the current ML users is like they have a lot of data sitting somewhere in their storage, either in the cloud or on-prem. And when they are trying to train the model, they sample their data set because they can't take all the terabytes or petabytes of data on their laptop. So they sample, bring it to their laptop, train the model, and then version control that, version it. And so the versioning is very important is for ML reproducibility purpose. So let's say if you train a model and now you want to like train multiple times, run multiple experiments. Now you want to go back and see which model performed well, which set of data set. So you want to maintain the different versions of your data or for different experiments. And the versioning is also important for collaboration purpose. So like if you are running model on your laptop or on your own, you want to collaborate with your team. So you want to make sure they also know which data set was used for different models. And in certain industry for regulation purpose, you have to maintain what data was used to train your model. So you have to maintain all the history. So based on that, if the regulators ask for you, like, how did you get this output from your model, you have to prove it to them that this is the data set you used, this is the program you used, or model you used, and that's how you got the output from this model. And then, of course, for documentation purpose and running different experiments, see which experiment performs well. And when they are running this, training this model, they are doing over and over again. So they are sampling their data set, downloading into their laptop or local environment, and running the experiment. So that's the pain currently the ML users have, like just copying all the data, bringing it into a laptop, managing all the data set. It becomes a pain to handle that volume of data. So what this product provides, lakeFS, which is an open source product, it's providing a like Git-like capability on top of your data. So very similar to like if you have used Git, which is for version controlling your software, lakeFS does the same thing to version control your data. And I'll talk more about that. So lakeFS sits on top of your object store. It can be on AWS or any cloud, or it can be on-prem. Like there's a MinIO, there are a lot of object store on-prem also. So lakeFS sits on top of that, and it provides versioning capabilities like similar to Git. You can create your branch, separate branch to run your experiment from your production data set without impacting your production branch. And then also roll back, merge all the changes. So anything you're familiar with doing with the Git, you can do the same kind of thing with lakeFS, but on your data set. And then your tools can work directly through lakeFS or directly on the top of the object store. The only difference is, let's say if you are using S3 and you are accessing a collection of your data, one thing you will do here is add the name of the branch. It can be like main, your production branch or master branch, or it can be, let's say you're running multiple experiments, so it can be experiment branch. So you can just create a separate branch from your production data, don't change anything, impact anything in production, run your experiment in parallel to your production environment. And again, we provide the APIs as well as the command line, so you can create the, similar to like Git kind of commands, you can run to create the branches and do all the version control operation through the command line also. The way it works internally is, like, let's say we are managing a bucket, it's object store bucket, and each commit is the pointers to different files. So let's say you have terabytes or petabytes of data, millions of files. So what we maintain, we just maintain the pointers to those files. So we are not copying your data. We just have pointers to those files. So each commit is just a set of pointers. And let's say if you do a new commit, if you make any changes in your data set and you do a new commit, and the object store data is immutable. So when you change anything, it deletes a file and creates a new file. So the next commit is just another set of pointers to other files. So in this case, a new file was created and the previous file was deleted, but the previous commit is still pointing to the old file. So we don't physically or hard delete the files. We have the pointers to those files, so you can, anytime you can go back to your history or to previous commit easily. We also have garbage collection process, so if some things are very old, like if you define your retention policy, you can delete the historical data also. So in this case, like if you want to run your experiment in parallel to your production, you can just quickly, in a millisecond, create a separate branch from your production data. And the branch is, again, set of pointers. So we are not copying the data. So if you have terabytes and petabytes and you create a branch, it's just a millisecond operation. We are not copying any data. And for ML use cases, for reproducibility use cases, you can go back to history and see for which model run, what data set was used at what times. And it works with locally also. Let's say if you want to bring some data set locally and want to test a few things locally on your laptop or in your local environment, you can clone that lakeFS repository locally also. Not the whole repository, not terabytes or petabytes of data, but within the repository also you can select the which folder or which data set you want to clone locally on your laptop, and then you can run your model, test your model, and make the changes. Let's say in this case, if I change some file locally, where I delete a file and bring a new file, or basically update a file, it's changing just a new file and creating a new commit, and that file gets uploaded to the repository. So that's how internally it works. Again, lakeFS is all pointers to different files in your object store, and we maintain each historical commits, so you can, anytime you can go back and look into how your data set looked like. So this is kind of, I don't want to bore you guys with all the presentations, so now I want to show you live, like how it works in the real life. But before I do, any questions so far?
If you have data,
Mm-hmm.
when you commit, if I have data in my S3, and when I commit something, and if version control is not enabled, it is pretty much overwriting everything, right? So how this lakeFS will take care of those scenarios where the data is completely overwritten and it has changed, the data is completely changed, right? Even if you have a pointer, the data is now pointing to a new copy, right? So how lakeFS works in that?
So let me go back to the previous one here, previous slide. So here, like for example, this file got changed. So in object store, it doesn't change the file, it creates a new file. It's immutable, so it will not overwrite the same file. So the previous commit points to the previous file, and the new commit points to the new file. So both the files are maintained in the object store. So people think the data will grow over time. Yes, but you can define your retention policy, how long you want to maintain the historical data. So that way we maintain the pointers to each file. We don't physically delete. When you, let's say, delete a file, when you go through, use lakeFS, we do a soft delete in the object store in S3. Correct. So the lakeFS sits on top of object store or S3 in this case.
So a person going and manually deleting the data, then you pretty much lost it.
If you manually delete, yes, we lost it. So normally what people do is they lock it down their object store or S3. So you always go through lakeFS. The users cannot directly access the S3. They always go through lakeFS, so lakeFS can maintain the version, control it, who can delete or not. Any other questions?
So for the data usage that sometimes the people just delete or change a few columns or a few cells, that would create too much of a redundancy on the data.
Yes, correct. So some of the open table formats nowadays, like let's say Delta table or Iceberg, what they do is they break the data into a small chunk of files. So it's not a very big file. Like if you have, let's say, a terabyte table, internally it's not stored as a terabyte file. It breaks into smaller chunks of file. And so if you change something, so let's say one table, terabyte table might have 100,000 files internally. But if you change a column or something, it might change only, let's say, 1,000 files. So that's how we maintain those 1,000 pointers to those 1,000 files. Yes, if you have a terabyte file, and if you change that, it will be a new terabyte file. Any other questions?
So lakeFS can manage any size data.
Currently, yeah, it can manage any size data. We are not like dependent on the size of the data or type of the data. It can be any unstructured data. On the structured data, we don't support the relational databases. We support anything residing on object store, like Delta table or Iceberg or Hoodie. Those are open table formats residing on object store that we support.
If it is a structured data, you don't care, right? I mean, Postgres, SQL.
RDBMS, we don't currently support. Maybe in the future, yes, we might do, but currently we don't. So I'm going to go into the live demo. This is available on our Git repository. If you want to run on your own later, you can run that. So as I mentioned earlier, this talk is more focused towards the ML use case, like how ML users use the data set. So in this case, I'm going to focus on the image segmentation use case. So this is a link. If you want, you can later on install on your own. And it's available on the Git repository. Everything you can run locally also. Right now, I'm running everything in the Docker container. Let's talk a little bit more about what is in this demo. So this was, there was a context run by Airbus. Airbus ran a challenge where they provided a lot of satellite images. And you have to quickly find the ships in that images. So that was the contest done in around 2018. So they provide the training data set. So a lot of people competed for that. So I used the same kind of example here because it's a large data set. They provided about 200,000 satellite images for that project. So that's what I'm using for this. So what happened, like in this case, as I mentioned, there are a lot of satellite images. Also, they provide the image mask. So for training data set, they have like in the all the images, they will tell you where the ships are, how many ships are there in the certain images. So that masking information is also there. So that data set, in this case, is stored in the object store. It can be on S3 or any other object store. Right now, locally, I have everything running on my laptop. I'm using min.io, which is object store on my laptop. And then from that 200,000 images, when you're running it locally, you can create a local experiment branch and copy a sample data set. Let's say you want to copy 100 files or 1,000 files. You bring it locally. Then you do, let's say, data pipeline. So before it goes into the model, you might kind of clean the data set. So in this case, I'm using a medallion architecture, if some of you are familiar. So where you have a raw data, then it goes to bronze, silver, and gold. In this case, I'm converting into resizing the images, transforming mask into images, and then joining both the different data set and converting into gold data set. Finally, it goes into the PyTorch Lightning model, image segmentation model. It's a publicly available model, which I'm using here. And to transfer the data from Delta table to PyTorch Lightning model, I'm using a PyTorch library. So that's kind of high level what I'm going to show in the demo. Any questions on the demo? No? Okay, let's start. So again, as I mentioned earlier, everything is running in my local container here. So I have my Jupyter notebook, lakeFS also running, and the object store, which is min.io, running locally. So this is the notebook I'm going to use. Again, this demo is available on our Git repository if you want to run. So here are the samples. There are two types of samples here. One is image segmentation local, where everything runs locally on your laptop. And there's another one is image segmentation, where if you have data set on S3, or if you want to run with all the big data set, you can run in the S3. And also for scaling, if you want to take this model and run in the distributed environment in, let's say, Spark distributed cluster, you can do that too. So for demo, I'll be showing in the Databricks environment. I'll be using the Spark cluster running on Databricks. But I have local as well, as you can run the same notebook locally as well as in the distributed Spark cluster. Okay, so let's start this. So here, just quickly show you how the lakeFS looks like. If you have used Git, it's very similar kind of interface. You define your repository, which is stored in the object store. It can be S3 or any S3 compatible object store. Right now I'm using min.io locally, but it's S3 compatible storage. And so let's define my variable here. So you're going to create a new repository in lakeFS, pointing to the object store locally. So if I go back here and just quickly refresh this. So now I have this image segmentation local repository, which is stored in this local storage here, but it can be on S3 or any other object store. Similar kind of, very similar interface as Git. Here you can create the branches from your production data set. So if you have, again, terabytes of data, it takes milliseconds to create a new branch to run your experiment or run your testing without impacting anything in your production. Then you have your commits and uncommitted changes. And then for ML use cases also, you can tag your data set. So let's say at a certain time, you are testing or experimenting with certain data set, you can tag it. So in the future, you can refer the data set by tag. You can refer it by commit ID, but commit ID is pretty long text or hard to remember. So you can use the tag. So and you can refer your, let's say experiment 1, you ran in January 2024. So you can tag like that. And also you can compare your data set between your different branches. So let's say if you're comparing the changes which happened from your production data to your branch. So let's say you create a branch from your production and you change something, couple of files, so you can quickly compare what changes happened between those data sets. And we also do integration with Git. So Git is, you can use for versioning your code, let's say your notebooks or your any program, and then use lakeFS for version control your data set. So next thing I'm going to create is a branch here. So I'm going to start from my experimentation branch. So if I go into my lakeFS repository, into branches, I have this my local experiment 1 branch. So you can create as many branches for as many experiments you want to run from your production data. In this case, I'm going to import some data set. Like for quick, I'm going to just use 50 images in this case, but you can import as many as you want. Again, for the import, we are not copying the data. It's just, again, the pointer. So you have, let's say your data is stored on a huge data set and on S3 or any object store. When we import, it's a few seconds operation because we are just getting the pointers to those files. And now, let's say I want to clone this data set locally. So if I go here, I'll quickly show you, like if you clone, it's going to bring the data set from the repository to your local laptop. In this case, I just downloaded the 50 images, and it's stored here locally on my environment here. Right now, it's a raw data set. So anything I change locally, I can make all the changes locally and commit my changes. That will go into the repository. So everything is then stored in the repository. I'm going to run a couple of quick commands here. Next thing, let's say if you're making changes locally, in this case, I'm going to delete some images, add some images. So these are a couple of images I removed, and these are 3 new images I added to that project, to my local data set. Now I can add those changes into my repository as well as in the Git. So let's say Git is just used for the program, not for the data. So when you are committing your changes to Git, it's not going to commit your data files. The data files will get committed to lakeFS repository, while your program will get committed to Git repository. Just make sure I can read the data set. So I'm just going to read some of the images and bring into my Spark data frame. So again, as I mentioned earlier, you can take the same notebook, run in the distributed environment in Spark cluster also. Next, I'm going to just quickly run the data pipeline. So again, as I mentioned earlier, like you have raw data set, which you are converting into bronze, silver, gold. In this case, I'm converting those images from image set to the delta table to binary files, and then applying the masking on top of that, and then converting into to gold data set. So just quickly look into how the data looks like in images. So these are the satellite images, and these are the boats in that images. Like for example, in this case, this image has about 14 boats. So this masking information was provided as part of this training data set. Now, next thing I want to run, split this data set into like a training and test, 80-20 rule I'm using here. And then, as I mentioned earlier, I'm going to use PetaStorm library to feed this data set from delta table to the model, that PyTorch lightning model. So in this case, I'm running that model locally here with different parameters. But when you run at the scale in the cluster, you might do a hyperparameter optimization. You run with multiple parameters. So in this case, I'm just going to run into 2 different types of parameters here. So it's only running my experiment twice. And I'm also using right now integrating with MLflow, if you guys have used MLflow, to record my the training experiments. So in this case, I just ran my experiment twice. Next thing, I can save what was my best model. Like I did 2 experiments locally here, and then I can look into which was the best model based on the certain metrics, and then save my best model into the lakeFS repository also. Next thing, as I mentioned earlier, you can keep your code in the Git repository and commit your notebook, in this case, to Git, and then commit the data set into lakeFS repository. And now let's look into quickly like how the data looks like. So if I go into my lakeFS repository, after running those 2 experiments, I picked up the best model. So it has information about the best model here. I can see what was the parameters I used, what data set I used. All that information is stored in one place. So if in future, you can go back and look into all the different runs you did, different experiments you ran, what data set was used, what parameters you used. All that information is stored in one place. And from here, you can also go directly to your run in MLflow. So here, like if I go into this flow, I have all the information tags with the tag, like what data set was used. So this is my gold data set, which I use for my training purpose, what parameters I use for this experiment. So all that information is also stored in MLflow. And now I can take this data set and go directly to lakeFS repository. So in this case, I ran this model and I tagged this data set here for a certain tagging nomenclature you can use. So this is the data set I used to train that particular model. So your model is stored in Git, like the source code is stored in Git, but we store all the data set which was used for the experimentation purpose. But if you're running thousands, you can take the same notebook or same model and run in the distributed environment. Let's say I ran this same thing in the Databricks cluster. I'm not going to run this again, the whole notebook again. It's the same notebook, but you can run in the distributed fashion where you can use bigger data set, not the smaller data set I was using in my laptop. But let's say I want to use with 10,000 images or 100,000 images. I can run that in the scale in the Databricks environment, again, pointing to my lakeFS repository. So in this case, let's say I create this distributed branch, a separate branch where I'm going to train this model. So everything is reading directly from the lakeFS repository. The repository is stored in somewhere in the object store. And then it runs the model and also version control everything, what model was used with what data. So that was for the demo. Any questions? Thank you. Still digesting? Just quickly wrapping up, the benefits of lakeFS is one is storage cost reduction. A lot of time when people are running their testing, running their experiments, they are copying the data set. They have so many different copies of data, and it becomes very hard to manage after some time. So one thing the benefit we provide is storage cost reduction. It's about 80% cost reduction. And also the improving the faster time to market. So it's engineers have less time to worry about managing the data set, which is managed by the lakeFS internally. So you can focus more on the use cases and training your model or experimenting your model. And also reducing the risk. One of the use case, which is not very applicable for ML use cases, but for other production use case, you can roll back all their changes. So let's say you made some changes in your production data set, and you realized you made some mistake, and by mistake you deleted thousands of files or millions of files. With single click, you can restore to the previous state, and it takes milliseconds to restore. Again, when you restore, it's all the pointers that we use. So we are not restoring each individual file. We are just restoring the pointer to go back to your history or previous commit. So it's very quick to restore to the previous state. Again, as I mentioned, it's an open source project. Project is used by many large organizations, like some of the defense contractor, home office, and also the biggest phone maker in Bay Area. So they're also using the product. They use the Iceberg. They are the biggest user of Iceberg. So they use lakeFS to manage their structured data also. Any questions?
Real quick. So when you commit changes to files in lakeFS, you're storing only the delta to that file. Is that right?
No, so we're not storing the delta. The file, if the file changes, so it's a new file. So let's say if you have a terabyte file and if you change just one bit in the file, it's a new file. So in object store, it always creates a new file, even if you change a small one bit only.
Okay, but you're not just storing like the different bits. You're storing like an entire copy of the original plus.
Yes.
Okay.
The entire file is stored. We are storing it and then maintaining the pointers to those. So but when you run the diff for certain types of file, you can see what changes happen. Let's say if it is a CSV text file, which is, you can create the difference, then we'll show you what bit or what character change in the file when you compare those two files.
Over the period of time, if I'm using the same data again and again, with lakeFS, the data might grow, right, in the S3 bucket. So what do you define? A user can define the policy after some time, start cleaning the data?
Yeah, so as I mentioned earlier, there's a retention policy you can define, and the policy you define for different types of branches. So let's say if you're doing a test and you create a test branch, you can say for all the test branches, delete my data after a day. But my production data, depending upon your policy, you can keep for 2 years, 5 years, whatever you want. But any experiment you might just run, let's say experiments for regulation purpose, you might have to keep for a year or two. But you may not have to. If you don't have to keep, you can delete your experiment branch and delete that data set. If you change anything in that data set, define the retention policy to delete it. You can do through lakeCTL, through the UI also. The retention policy you can define from the UI or the command line. Any other questions? No? Good. Thank you. Thanks for coming.